I've had a busy week, but now it's time to get started on problem 7. First, we must check this curve, or the good reduction of this curve. I think we've done that before, but we'll just do it again then. So let's do it in projective geometry. So we have a function of x, y, z. So we're looking for common solutions to this equation and the partial derivatives vanishing. That was what not would occur. So would they have any common solutions? In case P is distinct from, or the, what it's called, I forgot the name. P is distinct from 2 or 3, then both x or y and z will vanish. But down here, if y or z vanishes, they both vanish. So that shows that when P is distinct from 2 or 3, it has good reduction. All points are smooth. So we have to find a point in case P is 2 and in case P is 3. So in that case, this equation falls away. So we have x equals 0. And then we can set z equal to unity. And then y squared is 48. Oh, that's 0. So we get 1.0.0.1. Oh, that's the center. And in case P equals 3, this equation is automatically fulfilled. So we get y or z vanishing, but then this vanishes as well. So it's just, we know y must be 0. Then these 3 are fulfilled. So what do we get up here? If we set z to 0, then we get x is 0, no solution. So let's set z equal to unity. Then we get x to the 3rd plus 16 vanishes. And then x can be minus 1. Or should we say 2? So we have the point 2.0 point unity. I'll just check with the affine curve. We have it here. 2, that's 8. And y being 0. 8 plus 16 is 24, that's 0, so yeah, that's true. So if the characteristic of the field is 2 or 3, then we have solutions which are points which are not smooth on the curve, and if it's not, then all points are smooth. Now we shall look at the numerator of Z, yes, and this factor, that's not the numerator, that's a factor in the L series, never mind, very little mistake, much smaller than those I make all the time. I prepared this question by writing up the result of problem 21 in paragraph 2.2, which we have here. So let's take P is equivalent to 2 modular 3. Then the factor is 1 plus pt squared. Did they already change it to, yes, they did set t equal to p to minus s. Yeah, we'll just write t here, t squared. Now what's that? Isn't that true? Yes. And now so I wonder how the primes split in this is a little weird. This is prime like 5 or 11. What we have to do here is do what was the start of section 4 with the Gaussian integers. Now we have to do the same, show that that this makes sense in Q extended with omega, the third root of unity. I think the primes in here, these primes are inert, so let's assume that. So the norm of the prime is p squared, and the degree of the prime now what was the degree of the prime? Damn, I forget that. I'll just make a break when I look at that up. I have looked it up, and the degree here, in case the prime is inert, then it does lie in the field, so its degree is unity, and when it splits, then the prime is product of two elements in the field, so the degree is, or was it the other way around? My God. Interesting confusion. I'll make a little longer break and look it up again. Well, it's right what I'm saying. I don't know why I get confused. So we are not going to use this at all. We are going to write it as 1 minus I square root p, and then what was it, t we should use? Well, let's take t here, of course. Squared. No, yeah. And then we take what p is equivalent to unity, modular 3. Well, it's important that we get what C actually becomes. Minus A is minus 16, so that's chi2 of 16 times the real part of x3 of minus 64, j of chi3 by chi3. Now, this guy will lie in this field, that's why it becomes interesting, but let's reduce this a little. 16 is a square, so chi2 is unity, and x3 of minus 64, that's a cube, minus 4 to the third, so that's unity as well. And we had a problem earlier where we should compute this. And I did it for q equals 4, 7, and 13. And as always, we get the square root of q. I see I made a mistake here. This should be the modulo squared, and as well down here. So that's when we compute j, all the addends lie in q extended with omega, so the sum will lie in q extended by omega, and it will always be a square root. And that means that the factor becomes 1 minus 2 times the real part of, now plus the real part of omega of j of chi3 with chi3 t plus pt squared, and this is equal to 2 plus times 1 minus. Is that right? 1 agree. This minus this. No, that's not good. It should be a plus. So it's just squared, all right? No, that can't be, because then we don't get the real part, do we? Oh, it's the conjugate, of course. The 1, and when we add them, we get 2 times the real part, and the product is the modular of j of chi3 with chi3, which is, the modular is square root p, so the square of that is equal to p. So this agrees. That's part of the problem. Norm of p, that's p itself in this case. So that agrees. So the last point is that the unique generator, so that alpha p to p is equivalent to 1. They have a minus here, I have a plus. Oh, I do have a minus here. So I made a mistake in sign, which will come up. Well, let's start on the last part. So minus, so this is we'll just write it in the form. So it becomes 1 to minus ip square root p squared t squared this is the norm of the norm of the prime, the ideal generated by the prime. Then we must, that is p, and then it must be to minus s. So I've already, so we can't say that it is equal to it when we make the change of variable. It maps to. So it becomes t to minus s. So yeah, we need in this case to see that I square root p the prime is p. So h1 minus p norm of the ideal of p to minus s. Yes, I'm just confused again over the same thing. So I really need to be quite sure about this before I continue. Well, it was just confusion. In this case, we have AP to degree of P equals minus P, because AP was I square root P. And we must show that that this guy is the unique generator of P, such that it's equivalent to 1 modulo 3. So we have 6 generators. And P is equivalent to 2 minus modulo 3. So the only one we can have, that's when minus omega to the ith equals minus 1. And that happens exactly when I is 3. Well, P is equivalent, so this is equivalent to minus 2, that's 1 modulo 3. And the other ones, they cannot be lying like and and we have 3 being far away, so it's one of these guys, and it turns out to be this one. All right, now when P is equivalent to unity modulo 3, then what? Then we need to show that this guy or minus this guy is equivalent to and doing that, in order to be able to do that, we need to look into J itself. So let's just start on it. I have no confidence that I'll be able to carry it through. So we are working in the finite field of order 3, of order P, and then we have the character of order 3, non-trivial character of order 3. And we need to find out how it works out. We'll just call it J. can't use A. N. Example considered in the book, which was in section 2, they were paired, but now we are working modulo 3, we should find triples giving the same. Yeah, I was just thinking about pairing them like they did in the book, but then we get 2 times something plus, and then p plus 1 halves here, squared. That doesn't seem like going anywhere. So we're at a point where we need an idea. There is a saying that when you don't know what to do, you have a choice. You can spend 7 days in the laboratory, or you can alternatively just do 1 week in the library. I tried to do 1 week in the library today, and it turns out that we did work a lot on this problem already after section 2, in the problems to section 2. And B here is exactly what we need. And oopsie, I did prove it here, inspired by the example Q equals 13 that we already had done at the time. I was able to prove that J of chi3 point chi3 comma chi3 actually was equivalent to -1 modulo 3. All right. So solved. Now the next point is to check the Euler factor when p is 2, and they have some interesting comment here which surprised me quite a lot. What I'll do is that I'll just count the number of points on this curve when p equals 2 and r is 1, 2, 3, 4, 5, etc. And then the rewriting as this curve should give the same number of points. I guess the problem is that working with this curve, it's difficult to compute the number of points when p equals or q equals 2 to rth. So I'll just look into it by practical computation, and then tomorrow I hope to get some time to show what I found. Good morning, April the 7th. I said I would count the numbers of this curve and this curve when q was the power of 2. So we start with p being 2, and then counting the numbers of this curve, which is the one we're interested in. And there we do get That's actually q itself, 2 to the rth plus 1. It may be transferred into this curve. So we count the numbers there. And you can see here it's y squared plus y equals x to the third. And it's the projective solutions I count. I started setting the accumulator to unity. And there we get this guy, which is something different. And we have solved this before, really. I just checked the result. Now, to find that the curves are actually, that there's a rational map from one to the other, I don't think I solved this at the time, really. It was strange. We of course must multiply by 16. So in here we get a factor. That's annoying, it's gone. There we go. No. 8y plus 4 squared equals, and then 64x to the third and that means the map must be x point y maps to 4x 0.8y plus 4. That's of course a birational map, but in characteristic 2 it doesn't make much sense. Every point here is mapped to the center, the unit point on the curve. And then we need to find the zeta function for this curve. It's 1 plus 2 squared when the prime is 2. We did find that. And you can see it was not quite easy to find. I had to use the special lemma, whose name I forgot. Something Davenport, I think. Yeah, has a Davenport relation. Right. So let's get back to the problem now. Oh, there's yeah, that's where we are. And that's exactly what we have here. Now there is a question why we should work with that in case p equals 2, but then not try to find it when p equals in the prime 2. But I've found that Neal Koblitz is a very nice man. I think the message here is that it's a bit complicated to check the family of rationally equivalent curves and prove that for all of them, when p equals 3, it's a singular curve. We won't do that then. Now, with the Euler factor, blah, 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 smooth curve, yes. Now, to start on point 3, you see there's the unique sixth root of 1, so that, and we actually did prove this already. That was in problem 18 of section 2. Here we have it. I made light of it when I recorded last time, because I felt it was pretty obvious, but actually it is not. It needs to be proven, of course, and we did that already. Therefore, we are able to it's annoying, I can't see the pen. I have the problem now that I can't see the pen in the on the whiteboard. Therefore, I'm unable to write anything. But I wanted just to finish part C of problem 7 today. Now, we have found that this equals x times the character here, which is a character modular 3 on on Z extended by omega. So that's alpha to p that just equals x times chi of x. And then it's just a question of the expansion. And when we get this sum over ideals, and then it's a principal ideal domain, but when we sum over all the integers, we get every ideal 6 times, because the group of units has order 6, and that was the factor I forgot in problem 6. Right. So I would have liked to start on part D, but unfortunately I have a technical problem. It was difficult to me to find out exactly what was meant by this, because the dual lattice to set extended with omega was exactly this lattice 1/3 times. But reading the problem or the question sometimes led me to believe that we are dealing with the ring Z extended with omega modular the ideal generated by 3. And then this was a little strange. We have to work out what it actually does. So the trace of a plus b omega divided by I square root 3. That took a little thinking as well. That the trace is 2 times the real, so when we divide it, it's actually twice the imaginary part. And the imaginary part, they come out with a factor of square root 3. So now it makes sense. So it's, never mind the imaginary part, yeah. That's b halves. Oh yeah, square root 3, which eats square root 3 here. So it actually just becomes b, which of course is an integer. So now it makes sense. And that means, of course, it's an additive character. And on the ideal larger than 3, it must be non-trivial. So the ideal larger than 3 it's generated by 2 plus omega. Oh, and 2 plus omega psi of that, there's B is unity, so that means it gives omega, and that's distinct from unity. So that shows that it is a principle. Before embarking on the calculation, I think I need to specify something about the character chi. Which maps the entire ring into the third roots. What would I like to well, first of all, its definition. Is it a character? It's defined by x times chi of x is equivalent to unity modulo 3. So is it a character? Oh. Two, is it modulo 3? And 3, is its conductor? Or is it principal? Or was it called primitive? I think it was called primitive. Of course. So that its conductor actually is 3 and not yeah, that's the ideal here. So it's defined this way. The way I would have defined it if I hadn't seen this is to define it on the prime numbers and then defining it to be multiplicative out that from that, and then because then we know that it is a character, and then prove that this holds for all numbers. That seems primitive or simple, and then but now we go the other way. So assume that A chi A, B chi B, and AB chi AB all are equivalent to unity modulo 3. Now my idea is to consider the number A chi A, B chi B divided by AB chi AB. a priori it lies in the rational numbers. Yeah, and it's of course given by the definition that it is the sixth root of unity, so that chi is a root of unity, and that means that this actually lies in the ring. Not that ring. Of course, we'll just correct that. And then, since all of these are six roots, that's a multiplicative group, then this is a sixth root as well. And since they are all equivalent, or what? Yeah, these are all equivalent to 1 modulo 3. Oh, maybe we should start with this. This is an integer. Then we extend it with AB. They are each equivalent to 1 modulo 3. Therefore, this is equivalent to 1 modulo 3, and the only unit being equivalent to 1 is 1 itself, and that means that this equals 1, and then it follows. So that's proof that it's a character. Next, we have to compare n, chi of n, with chi of n plus 3, and hope that they are, and we use the same trick. And this equals n chi n plus 3 plus 3 times chi n plus 3. So that means that n, oops, no parenthesis is needed. Why do I add them? It's the difference. Are equivalent to naught modulo 3. 3 divides this. And n is co-prime with 3. So that means that 3 divides chi of n minus chi of n plus 3. And they are units. And I don't know if there's a detail to it, but going through units I can see that just they have to be equal for the difference to be naught. This ideal may divide a difference between two guys, but not 3. So that implies that chi of n equals chi of n plus 3. Oops, and now the same should be done with omega. If we add omega, 3 omega, that's the same. All right, and that was point 2. So this is 1, this is number 2, and number 3, that it's primitive. That was very difficult in the case of y squared equals x to the third minus n squared x. But that was because we had to do it with an infinity of values of n, with an infinity of curves. Now we just have one curve, so the only ideal dividing 3 is I. So let's look at chi of 2 plus. We can just take this guy. And add 1. So let's take chi of 3 plus omega equals chi of omega, and that's 1 divided by omega. Which is of course distinct from unity, meaning that chi is not trivial on 1 plus this ideal. Now I'm ready to compute this sum. I'll make a break and then make a table or a diagram with the values, and then we can compute it. I have now prepared the computation of g of chi. I wrote x, this is x, this is a plus b omega, a going from, I wrote 2, but then when I did it I thought I worked with minus 1, never mind, and then b going from minus 1 to 1. The blue guys are psi, and then I did chi. So let's take some of the examples. 0.0 here, chi of 0, it lies in the ideal, so it gives 0. And 1.-1, that's minus omega, it lies here. It must be multiplied by 1 plus omega to give unity. And that's of course minus omega squared. And let's take this one. You can do that yourselves. Let's compute the products. So minus omega plus unity plus, I don't write the noughts, minus 1 plus unity minus omega squared. All right. And of course, these two give unity. So we have 1, 2, 1, 2, 3. Well, this should be the preparation for the grand finale, problem 8, where we assemble a vast number of the problems into one result.